All right, so here we are, AP Calculus. This lesson is on volumes of solids of revolution. So we talked about volumes using cross sections in our previous lesson. Um, when we talk about volumes of solids, we're still talking about integrals, but now we're talking about revolution, okay? So we're actually revolving an area around an axis, okay? This is technically called the disk method. We're going to do something called the washer method a little bit later. But you know about integrals, okay? So think about this diagram right here, and if you're following along in your Finney text, this is on page 400, okay? Integrals, it would represent the area here, okay, underneath a graph. So this particular graph actually is, now I think I have it down here. Yeah, this is actually 2 plus x cos x. That's what this graph is labeled. That's the function, okay? And the area underneath would be the integral of that function, right? dx. Now I'm going to show you a little video here as, and I'm going to have to, I guess, cut and copy this. I can't go directly from here. Bear with me for a second. Okay. Let's go to YouTube, hopefully. Oh, we're a little bit slow here. Okay, so you want to check out some good videos on YouTube. This is where you want to go right here, Mr. MathWell. Let's put this in though. So I'm going to show this video, and this is me showing this video to one of my classes a little while ago. So I'm going to cut the audio. I'm just going to kind of walk you through. This is the lesson, and here's the video. Okay, so focus on the animation here, and this animation shows a graph. So here's a graph above here, this x squared minus 4x plus 5. Looks like between about 1 and 4. And if we consider the area underneath that graph from about 1 to 4 or 5, okay, we first learned about Riemann sums. Remember Riemann sums, the rectangles. And if you consider this, we're going to take this area right here, and this is the big thing right here. We're going to take this area, and we're going to revolve this area around a specific axis. In this case, we're going to revolve it around the x-axis here. Okay? Do you want to shut that? Okay, so in 3D space, this is what it looks like right here. Okay, I'm going to pause this right here as we move around. It makes a 3D, and it looks like a cone of some sort, like almost like a speaker. So again, here's my function right here. Here's the x-axis. Okay, working at this three-dimensionally. And if you were to revolve this shape, the area between the x-axis and this curve, if you were to revolve that around, spin it around, you would make a 3D shape that in this case kind of looks like a cone or something. Okay? So the essence of this lesson, and notice inside there, that's hollow in there, right? That's actually hollow in there. So let's look at another one. The essence of this lesson right now is to find the volumes of solids that are basically regions on the coordinate plane when they're revolved around some axis. So the x-axis is where we're going to start. We're going to take an area and revolve it around the x-axis, but they also could be revolved around the y-axis. So this case here is taking this area that's very similar to the one we were just studying before, and if you revolve it around the y-axis, this is the solid of revolution that you get there. Okay? And I think there's maybe one other example, but yeah, no, that's the last example. Okay, so you get this solid. It's curved going down into the middle there, but it's definitely a three-dimensional figure. Okay, so let's get out of there. Let's head back to our notes here. So this one right here, this kind of looks like a little bit of like almost a side profile of a fish. If you took this and used the radius, used the distance from the x-axis to the function as some kind of radius of a circle, then what you would do is you would be able to envision, I think, a disk, okay, a circle. And these circles are going to have varying radii, varying lengths of the radius. It's very small here. pretty large up here, right? And so if you took each point and revolved it around the x-axis, we would end up getting a solid that kind of looked something, you know, like this. This is what we would get, and it looked like this over here, okay? So the key to this is we're not talking about triangles or squares or rectangles. We're talking about circles now. So think about it. We have all of these disks, and they're all piled up three-dimensionally, and if we were to add up all those disks, we would get this three-dimensional solid. So solids of revolution are made when f of x is the changing radius. So the radius of these spheres, okay, or an infinite number of circles, I should say. Circles would be the 2 dimensions. Sphere would be 3 dimensions. But if the radius is the f of x, and we have a collection of these over an interval, then we can make a solid 3D figure. Okay? So solids of revolution are made when f of x is the changing radius. And if we were to compile an infinite number of these circles and stack them together, we get this three-dimensional solid. Okay, any questions there so far? Okay, so the nice thing about this is that all the work that we did with cross-sectional areas, we're going to be able to use all of that knowledge here for solids of revolution, especially when we're taking the full area and we're just revolving it around the base, like the x-axis. Super easy, okay? So if you recall from the other day, I'll just zip back here to the notes that we took the other day. Remember these notes right here? So the cross sections were squares, or they were right triangles, or equilateral triangles, or stuff like this. So when we filled in those notes, we ended up having, where are we here? We ended up having, you know, these sort of formulas, right? And so for this one, there is a formula very similar to the ones that we determined in these previous lessons. And those are going to be, that's going to be, have to do with a circle. So if I'm making discs, okay, we have the area of a circle or a disc is pi r squared. Okay, now think about this. We've turned areas into integrals before. So if I have the integral of pi r squared, let's say dx, because the little differential, so the width of these disks are bumped in the x direction, right? So here's the, if we're thinking about an actual disk, right? I've got a little width of this disk here, if I can draw that. And this is dx, so dx is in the x direction. So this has to be in terms of x as well, the r squared, because we have an x as our little differential there. Okay, so r, we said, was changing over the interval, and it is exactly equal to whatever the f of x is. So the integral from a to b, it's going to be a definite integral, right, is what this volume of this solid of revolution is going to be, and r is going to be f of x. So I have this, I have pi, this is times f of x squared dx. All right? And because pi is just a constant, we don't really have to include pi in there, do we? So I'm going to move pi out to the front here. Pi times the integral from a to b, whatever our interval is, f of x squared dx, okay? So, everyone kind of see that? Everyone see what we're doing there? Now, if we're taking a look at this example right here, and I think what I'm going to do is I'm going to just erase some of this stuff that I did here, okay? So hopefully you have that copied down. I'm going to make some room here, and we're going to take a look at this exact example, and we're going to find the volume of this solid of revolution from -2 to 2. So a is going to be -2, b is going to be +2, and the function is given up here, okay? So here's now where we take this formula, and I'm going to fill in the values. So -2 goes down here, +2 up there. The function is 2 plus x cos x. 2 plus x cos x. And that's going to be squared dx. All right. Now, we're not. I'm not going to make you solve this integral manually here. Okay, we're going to use our technology. So if you have a graphing calculator, you know what? Maybe I'll do it on the graphing calculator here, because for the AP exam, you'll be able to have a calculator like this. You're not going to be able to have Desmos up on your screen, right? We're not going to be able to get your computer out and plug in Desmos. It has to be a calculator like this. If you do not have a calculator like this wherever you're watching from, then please just watch the keystrokes here. If you have an application on your computer like I do, that would be most handy. But let's see if we can kind of get through this here, okay? So I've got some stuff here that I need to clear from last class. Okay. Now what I'm going to do is I'm going to go from the home screen here, and I think I did this in the last video. Correct me if I'm wrong, but we're going to go to the home screen, and I think in math. Nope. Yeah, math. Or was it calculate? No, it's math. Yeah, on the math button. So FNINT, there it is, number 9. So hit your math button on the TI-83, number 9. Okay. So once you have FNINT, function integral, you're going to type in the function itself. 2 plus x cos x. And yeah, you're going to need to be in radians. Okay, so you're going to close the brackets off there, looks like. So here's your function, 2 plus x times cos x, good. Oh, to the power of 2, or squared. Okay, good, we need that. And then you need to tell your calculator this is the integral, of this dx, so put in comma x. Then everything gets separated by commas here. Now you put in the lower limit of integration, so -2. Another comma, should be +2. Okay, so finite, okay, squared. Oh, times pi. Okay, so I think I'm going to have to go back. Actually, we can just multiply by pi afterwards, I guess. So, oh, something I didn't like. Do I have one too many brackets there? Quite possibly. Cos x. Okay, so we got that fixed up here. Just make sure that the proper number of brackets. That's the only thing I don't like about this calculator is all the brackets you got to put in. Okay, so I guess what we have here is we have the integral itself before the times pi. This integral itself, that area is represented by 16.686. Okay. Now we'll multiply by pi. Take that and multiply by pi. And we get 52.4288, which I believe is the number we are looking for. Okay. So V equals 52.488 units cubed. So we have an area here. That's the integral of this only, dx. That's the area here. And because we want to make this into a series of circles, we want to multiply by pi this squared. Okay. All right. I hope you're following here. This is pretty straightforward, I think. The difficulty, well, the next level will be is if we don't rotate it around just the x-axis, but I'll show you how to do that right now. So credit to Mark Sparks. We're going to use some of his material here. He's awesome. This material is awesome. You should have a handout in front of you. If you don't have this handout, it is on my website. If you just go to, this is pre-calculus. If you go to mrmathwell.com, and my calculator's pretty slow. So here's just a snapshot of what I did with the Desmos. So you can get a link to the Desmos calculator just there. Actually worked really well. This is a question from the last assignment. But we go down, where are we here? Okay, should be coming up here. So there should be, I do have right here, the cross sections and volumes notes and assignments. So you want to download from there, and you'll have you'll have this in front of you, okay? All right, so this is what we've looked at, but as I mentioned, what if we want to rotate not around the x-axis, but around another horizontal sort of line, okay? So we can do that, and that's sort of the next level. Everything's pretty straightforward up to here. So notice that the axis of rotation is the x-axis. That's what we've done so far. And the bottom of the function is the region up to the x-axis. That's what we did before. So before we did a question like this, right, all the way down to the x-axis, and we can rotate that around to all these little circles, right, and we can get this three-dimensional, looks like this, right? So that's what we did before, but what happens if we don't want this, and we want to rotate it around, not around the x-axis, but we want to rotate it around something like y equals 1 or something like that. So we just want to rotate this part, this area. Okay? Now if you can envision this, this will be looking something like this, but this middle part would be hollow. So there will be, basically this is like washers. They'd be like discs with holes in the middle. Can't quite see that real well, but this would be the hole in the middle. And that's going to happen all the way along, isn't it? Okay, hole. This is going to be a hole. And you're going to have your solid of revolution all the way around that, right? Looks something like, well, like that. Okay? This middle is going to be hollowed out. That's going to be hollow. Can you kind of follow me there? You kind of see that? Okay. So it's hard to envision. I know it's hard to envision, but there's going to be a hollow cylinder in the middle here as we wrap this around. Okay? So it's around so let me just read further. Imagine from what the solid would look like if the x-axis were the axis of rotation. The x-axis is the axis of rotation, but the bottom function was a line. So we could rotate it around a line, or we could rotate it around the x-axis, but not include the bottom area. And that's, I guess, what I'm referring to in this case. Okay? There will come a time where we will be reflecting things about other than the x-axis. I guess this is not that time. But if we have a function, let's say we have this function. If I want to rotate it around the x-axis, yeah, it looks something like this, right? This three-dimensional. But if we rotate it around y equals -2 or something, if we rotate it about this axis, then it actually sort of is like this, right? And we have this sort of larger thing going on here with a big hole in the middle, right? So we're not going to include this bottom area in the solid that's rotated, and that's, I guess, what this first example is. So to find the volume of this solid, we would find the volume of the whole solid that we found previously and then subtract out the solid in the form of the cylinder. So we could find, we're just going to find this yellow area and rotate that around. And how we're going to do that is we're going to find this whole area down to the x-axis, but then we're going to subtract this part. Okay? Or we're going to find the volume of the solid all the way down to the x-axis, sort of like we did with this example. But if we wanted to cut off this bottom part, we would take away this volume, okay? And that's really what we're doing. So we just have the kind of the outer sort of shell. All right, let's just keep going here. Keep reading. So the volume is going to be the integral. We're going to do pi. So we're still going to do a pi r squared, but we have to do the integral from a to b of the outer function minus the axis. Okay. In this case, we're doing y equals 1 squared minus the inner function minus the axis. So we're still rotating around the x-axis, I should say. But we're going to take this big solid and then we're going to subtract the inside part, the inside solid. Okay, and that's how we get what we're looking for. So the outer function is always defined to be the function that's farther from the axis of rotation. So we'll have to remember that. In this example, If we are rotating around x still, the outer function is the one that's farthest away from the axis. The inner function would be the one that's closest. Okay? So in this case, the axis of rotation still is the x axis, but for the volume of this solid, that would not include this kind of bottom part here, not include this part, but only this above part that we rotate around the x-axis to make that hole in the middle. The volume would look like this. It would be pi times the integral from a to b, whatever a to b is. And then we would have to make sure that we did the outer function f of x minus the axis of rotation, okay? And it's still going to be y equals 0. And then subtract this axis right here. If this is going to be the lower function, y equals 1, then we would do 1 or whatever that is minus 0 squared dx, okay? And yeah, we'll do some examples here in the next few minutes of that. Okay, so the new thing is obviously this axis, if it's something other than the x-axis, or if we have a bottom function, okay, that we're restricting this region that we're rotating. That's important. Also, we are making sure to remember to subtract away the volume that would be represented by the opening in the middle. Okay, some examples. Let's just work through some of these examples here. So consider the region pictured to the right. So here is this should be on the next page of your notes here. The region that's pictured on the right, so that's this region right here that's filled in blue. We have y equals x plus 2 is this line right here. And we also have y equals x squared, okay? So there's a region that's enclosed between those two graphs. How do we find the volume of the solid formed when the region is rotated about the x-axis? So the axis of rotation is the x-axis right here. So we're going to take this piece and we're going to flip it around the x-axis. So if you can kind of envision, the cross-section would look something like this. Right? Kind of poorly drawn. But here's the flip. It flips around and it goes all the way around here. Okay? And all the way around to here. But it does not include, it doesn't include this inside portion. And it doesn't include this right here. Okay? It just includes, this would be kind of like that cone that we saw. Okay? So picture this. It's just this blue part that's pivoting. Really, for the most part, it's pivoting on the origin here. Okay, it's sitting on the origin, and we're just flipping it around the origin. And whatever space that this region here, whatever space that it touches, that's going to be filled in as a solid. All right. So find this volume. Okay. So the volume is going to be represented by pi times the integral from. And on this diagram, thankfully, we do have the intersection points. So we've got to go from -1 all the way to the other x value of the intersection point, +2. So from -1 to 2. So we want to include all of these, disks or whatever. And again, we're going to do the far function that's furthest away from this axis of symmetry. So that's x plus 2. So we've got to go x plus 2 minus, what's the axis of rotation? Well, that's going to be y equals 0. We have to square that. Again, we're just following the format that this format up here, or really right here, at the very top. And so minus x squared minus 0. 0, again, is the axis that we're rotating around. Squared dx. All right, so let's simplify this. X plus 2 squared. It's going to be x squared plus 4x plus 4 minus x squared. sorry, x to the fourth, my bad, minus x to the fourth, x squared squared. And so we could find the integral of this now. This is easy. These are all separate terms. And so let's find the integral of these terms right here. So that's going to be x cubed over 3 plus 4 over 2x squared plus 4x minus x to the 5 over 5. And we're going to take that from -1 to 2. Sorry if you don't have a lot of room to do this, but we probably could, let's simplify this a little bit more here. So again, when we evaluate this definite integral, we evaluate this whole thing here at 2, and then we subtract from it the value at 1. So 2 cubed is 8, so that's 8 over 3, plus, this is 2 times 2 squared, so that's 8. Yeah, 2 squared is 4, okay, so that's 8, plus 8 minus x to the 5, that's 32 over 5. Okay. So we'll subtract from that. This is -1 over 3 minus 6 over 3 plus 1/5. If we evaluate all that, and I'm running out of room a little bit here, but this volume ends up to be 72 over 5 pi. Okay, so we'll add up this together. We'll subtract this, multiply it by pi. We should get a simplified version of 72 over 5 pi. Okay, so I'll give you a chance to finish working that out. Show your little steps in between there. Make sure that's the right answer. Okay, so that's confirmed that answer. The next portion of the notes here says this. Now this is where things change a bit. Find the volume of the revolved region, okay, the solid of revolution. Find that volume when the region is rotated about the line y equals 4. Okay, so here's where we'll get into, this is going to be really important, right, when we subtract the axis that we're revolving around. So right now, here's y equals 4. So try and envision this. Okay, try and envision this. We are taking this solid and we're wrapping it around this way. Okay, so I don't know if I can draw this very well, but think about this. All right, this is the top part. This is, you know, and then there's it's wrapped around here. Okay, like this. Okay, so we have a hollow part in the middle. Obviously, this kind of part in the middle here is hollow, but we do have this solid here, and it'll kind of look like again kind of like a cone. Okay, but we're flipping it up, and we're revolving it around y equals 4. Okay, so we can do that. We just have to kind of rest on this right here, and the axis again is where we're revolving this solid around. Here it was the x-axis, not y equals 1, the x-axis. So I'll get rid of some of this here now so we can see this a bit better. So what we want to do is use our format. V equals pi times the integral from, I guess we're still at -1 to 2, because those are the intersection points still. And then we want to do this. So we want to do the function that's furthest away is this parabola, right? So we want to do x squared minus the axis of rotation. So x squared minus 4. x squared minus 4, all squared. Minus the inner function is x plus 2 minus 4, axis of rotation, squared dx. Okay, so take a moment and just digest that. Okay, here's the outside, the far away function. That's the one that's listed first. And here is the closest function. That one's listed second. And we do subtract the axis of rotation. And that's the format. All right, so the volume is pi times the integral here. I'm going to simplify this. This is going to be x to the 4th minus 8x squared plus 16. That's what you get when you square this. Okay, so I don't have all the steps figured out here or written out, but your answer should be 108 over 5 pi. As I mentioned to my class here, we'll work on manual integration when possible. This is just a polynomial, should be able to do that manually. Manual evaluation, and try and keep your fractions in terms of pi for exact values as well. So 108 over 5 pi. If you did use your calculator to find the decimal form of that, let's see, that is 108 divided by 5 times pi. Should be about 67.858. Okay, 67.858 or so. Okay. All right, let's do our last example. So here's our last example where we're talking about an axis of rotation that is the line y equals -2. Okay. So now we're taking this and we're revolving it around this line of y equals -2. Okay. So if I'm drawing this, or if I'm trying to help you envision this, this bottom section right here, this bottom point right here of this graph is actually rotated all the way down to here. And so we have, this is what this looks like. Okay? So this thing is rotated around and it follows through space. Okay? That's that corner that follows through space. This corner follows through space. And then we have this big open bit in the middle. So again, another kind of cone shape. I wish I had the animation for you, but that's the best I can do to help you understand that. So we have this big hole in the middle for sure. A big space in the middle really there. Okay? So let's work on that. What does that look like? Very similar to what we've done here before. So I'll use black here. Nope, I'll use blue. So we're going to look at the volume here for this solid is going to be pi. We're going to use our integral from -1 to 2. And we're going to look at the outside line here, I guess, which is the x minus 2 line, right? That's the furthest away from the axis of rotation, so we'll start with that one. X plus 2. And then we're going to subtract our line of rotation, minus -2. Squared. That's the first part. Okay. The function that's the farthest away, x plus 2, minus the line of rotation. Okay. Minus the inside, the function that's closest, which is the x squared function, minus -2 as well. Squared dx. So we can simplify this quite a bit. That's actually going to be x, plus 2 plus 2. So that's going to be x plus 4 squared minus x squared plus 4 squared, I guess. Okay, so slight change here, x squared plus 2, not plus 4 there, my bad. Okay, so I'll continue on here. Okay, so I don't know if you took the time to do that. Here's everything just kind of manually. If you want to type a bunch of this into your calculator from this point or whatever, you go right ahead. But the exact answer should be 162 pi over 5 for that volume. So I think we'll end this lesson here today. We'll give you a chance to do some homework questions here, which would look like this right here. So if you're watching this video, if you want to take a look at these questions, see if you can do these questions. I'll probably give you some answers in a little bit. So there's first 3. Here's 4 and 5. It's a tricky one. There's 2 different regions here, R and S. 2 different regions right there. And so you're going to have to take those separately, actually. So there's a bit of work with 4 and 5. It's a challenging one. And then here's the second, the last 2 questions here. Okay. All right, so the answers to these homework questions, so I'll put these up here. So number 1 is 1.949 you should get for an area there. Also for number 2, 34.199. For number 3, your answer should be 17.099. Okay, so for number 4 and 5 here, points of intersection, and we'll do this on Desmos or our graphing calculator. This first point, so we'll name that point AB. Let's say AB. That's going to be 0.178 and 0.781. And then this point over here, we'll call that CD, I guess. And that's going to be equal to 1, comma, 0.25. So the 1.25. All right. Okay. So that's 6 and 7, I guess. I'm going to give you some answers for 6 and 7 as well. So let's do that. This AP question here on this handout, pretty tricky. Really tricky. I would say that's a great challenge if you want to take a look at this one. I will be working through this one probably in a separate video in a separate class, but if you want to take a look at this one, I'll save that one for a little bit later, okay? So this question here, which is mislabeled, that should be 6, this should be 7. And the answers to those ones, if you had a chance to do that. This one's not that tough a question, I don't think, given what you guys know now, but 2.979, and this one should be 4.559. All right, so that's your that's the lesson for volumes of solids of revolution, and yeah, so we will talk about rotation about the y-axis as well. That's going to be in another lesson, another day. So volumes of solids of revolution.